Problem 25. For a positive integer n and non-zero digits a, b, and c, let a sub n be the n-digit number, each of whose digits is equal to a. Let b sub n be the n-digit integer, each of whose digits are equal to b, and let c sub n be the 2n-digit, not n-digit integer, each of whose digits is equal to c. What is the greatest possible value of a plus b plus c for which there are at least two values of n, such that c sub n minus b sub n equals a sub n squared? So we can get closed form expressions for these. This is pretty crucial. So a sub n is equal to 10 to the n minus 1, which is n digits of 9 times a over 9, so that we replace each of the 9s with a's. Similarly, b sub n equals 10 to the n minus 1 times b over 9, and c sub n is equal to 10 to the 2n, because it's a 2n digit number, times c over 9. And so when we plug this in to our equation, we have 10 to the 2n minus 1 times c over 9 minus 10 to the n minus 1 times b over 9 is equal to 10 to the n minus 1 squared times a squared over 9 squared. We multiply everything by 81 over 10 to the 2n over 10 to the n minus 1, just to cancel and simplify. So this becomes 10 to the n plus 1 times 9c minus 9b, which is equal to 10 to the n minus 1 times a squared. So then this ends up being 10 to the n times 9c plus 9c minus 9b is equal to 10 to the n times a squared minus a squared. And so for n equals 1, a squared, it can be big enough to affect like the 10 to the n values, but we need to have this be true for two values, two positive integer values of n. And for n equals 2, 10 to the n is greater than a squared. 10 to the n is greater than a squared. And so basically is greater than a squared minus 9c minus 9b. Or like plus whatever. Basically, you can't get a big enough difference in like the non-10 to the n terms to affect the 10 to the n terms. So that basically ends up giving us that for n greater than or equal to 2, and then we have to have at least one such thing to have two values of n for which this is true. 9c equals a squared, and 9c minus 9b equals negative a squared. So this means that b equals 2c. So basically, we have two equations. We've reduced this entire thing to just solving these two equations to maximize a plus b plus c. And we can choose the biggest we can hit is a has to be a multiple of 3 in order, because like 9 divides a squared. So a equals 6, c equals 4, and b equals 8 is as good as we can go without getting above 10. And then adding that up, 6 plus 4 plus 8 gives us 18. And we are done with problem 25.